In episode 17, titled Central Limit Theorem, Why Averages Behave and When They Don't, the goal is to use the central limit theorem to reason about sampling and uncertainty in a way that helps you choose correct answers under exam pressure. The central limit theorem shows up in DataX not as a demand for proofs, but as a reasoning tool that explains why many statistical methods work and when they become questionable. When you understand it, you can judge whether normal approximations are reasonable, whether uncertainty claims are trustworthy, and why sample size changes the stability of your estimates. This matters because the exam often presents scenarios where someone wants a quick conclusion from a sample, and the best answer depends on whether the sampling conditions support that conclusion. You are going to hear a simple statement of the theorem, but we will spend most of the time on the boundaries, because boundaries are where test takers lose points. The purpose is to make you comfortable using the theorem as a professional intuition, not as a memorized slogan. Before we continue, a quick note. This audio course is a companion to the DataX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. Stated simply, the central limit theorem says that the distribution of sample means tends to become approximately normal as sample size becomes large, even if the underlying data distribution is not normal. The important phrase is distribution of sample means, because the theorem is about what happens when you repeatedly take samples and compute an average, not about what happens to the raw data itself.
In practice, this is why averages behave nicely, which supports many confidence intervals and hypothesis tests that assume normality in the sampling distribution of an estimator.
The exam may not present it in formal language, but it may describe taking repeated samples, averaging results, or relying on normal approximations for estimates, and the central limit theorem is the reason those steps can be defensible. This is also why analysts often work with aggregated metrics, because aggregation can make inference more stable and more predictable. DataX rewards learners who can articulate that the theorem is about means becoming well-behaved under repeated sampling, not about magically turning the world into a bell curve. A critical clarification is that the central limit theorem applies to means and related averages, not to every distribution shape and not to every statistic in the same way. The underlying data can remain skewed, heavy-tailed, or otherwise non-normal, and the theorem does not fix that distribution in the raw sense. What it gives you is an approximation for how the mean behaves across samples, which is a different object from the distribution of individual observations. This matters because exam scenarios may describe very skewed data, like transaction amounts or response times, and learners may incorrectly assume that the central limit theorem makes everything normal and therefore safe to treat casually. The correct reasoning is that the mean can have an approximately normal sampling distribution under the right conditions, but the raw data can still be ugly, and that ugliness can influence how many samples you need and how reliable the approximation is. The theorem supports inference about averages, but it does not remove the need for thoughtful summary measures and robust methods when the data shape is problematic. DataX rewards this distinction because it is a sign you understand what the theorem does, not just its name. The central limit theorem also helps explain why standard error shrinks as sample size increases, which is one of the most useful practical consequences for exam reasoning. Standard error describes how much a sample mean would vary across repeated samples, which is the stability of your estimate. As sample size grows, each average incorporates more observations, which tends to cancel out random fluctuations and reduce variability in the mean across samples. That shrinking of standard error is why confidence intervals often become narrower with larger samples, and why tests become more sensitive when you have more data.
The exam frequently tests this relationship conceptually, asking what happens to uncertainty when you increase sample size, or why a result becomes more stable with more observations. The key is not to memorize a formula, but to understand the logic. More independent information reduces the randomness of the average. When you hold that logic, you can answer many uncertainty questions quickly and confidently. Not all data distributions play equally nicely, and heavy tails are a classic case where you need larger samples for stability, which the exam may test through scenario cues. Heavy-tailed distributions have a higher chance of extreme values, meaning a few large observations can heavily influence the mean and make the sampling distribution slow to settle into a normal shape. In practical terms, this means that the enough samples part of the central limit theorem can be much larger than learners expect, depending on how variable and extreme the underlying data can be. If a scenario describes rare but enormous spikes, highly variable values, or outcomes dominated by occasional extremes, you should be cautious about assuming that a modest sample size gives a stable mean. The theorem still points in the same direction, but the speed of convergence toward a normal approximation can be slow, and uncertainty can remain substantial. DataX rewards this caution because it reflects experienced judgment about real-world data, where not all averages become stable quickly. When you recognize heavy tails, you become more open to robust methods and more conservative about making strong claims. The central limit theorem connects directly to confidence intervals and hypothesis tests because those tools often rely on assumptions about the sampling distribution of an estimator. When you construct a confidence interval for a mean, you are using the idea that the sample mean has a sampling distribution that can be approximated as normal under appropriate conditions, which allows you to translate standard error into an uncertainty range. When you perform a hypothesis test about a mean difference, you are often using similar logic, comparing an observed statistic to what would be expected under a null hypothesis, using an approximation that depends on normal behavior of the sampling distribution. The exam often frames this connection indirectly, asking whether normal approximations are appropriate or whether inference methods are justified given sample size and data behavior. When you can tie the theorem to these tools, you can explain why they work and also why they might not work when conditions are violated. DataX rewards learners who understand that confidence intervals and tests are not magic. They are built on assumptions, and the central limit theorem is one of the reasons those assumptions can hold. That connection turns the theorem into a practical checkpoint rather than an abstract fact. A common exam task is deciding when normal approximations are reasonable, and the central limit theorem provides a structured way to make that judgment from scenario information. If the sample size is reasonably large, observations are independent, and the underlying variability is not dominated by extreme outliers, a normal approximation for the mean can be a defensible choice. If the sample is small, the distribution is extremely skewed or heavy-tailed, or the data contains strong dependence, normal approximations become more questionable. The exam may describe a small sample from a volatile process, or may hint at dependence through repeated measures from the same entity, and those are signals to be cautious. The best answer in such cases often involves using methods that are less assumption-sensitive or collecting more data, rather than confidently applying normal-based inference. This is a judgment call, which is exactly what DataX is designed to test. Can you recognize when a convenient approximation is appropriate and when it is risky? When you practice this decision logic, you will find these questions become less intimidating because they reduce to a few key conditions. Independence is one of those key conditions, and non-independence can break the assumptions that make the central limit theorem useful in the way learners expect. If observations are correlated, such as time series points, repeated measures from the same subject, or clustered data from related units, the effective sample size is smaller than the raw count suggests. This means the average can remain more variable than you would expect under independence, and standard error estimates can be overly optimistic if you ignore dependence. The exam may describe data collected from the same users over time, devices reporting multiple measurements, or events influenced by prior events, and those are all dependence cues. In such scenarios, you should be cautious about treating the sample as a collection of independent observations, because that can lead to overconfident conclusions. DataX rewards learners who notice dependence and who choose answers that adjust design, use appropriate methods, or interpret uncertainty more conservatively. Independence is not a technical footnote. It is a core condition that determines whether central limit theorem intuition applies cleanly. Central limit theorem thinking also applies to aggregated metrics like conversion rate, which is an example of how the exam may connect averages to practical business outcomes. A conversion rate is essentially an average of binary outcomes, where each observation is a success or failure, and the sample proportion has a sampling distribution that can be approximated under suitable conditions. This supports confidence intervals and hypothesis tests for proportions, allowing you to reason about uncertainty in rates and differences between rates. The exam may present a scenario about campaign performance, feature changes, or user behavior, and ask whether an observed change in conversion rate is meaningful. Central limit theorem intuition helps you remember that the observed rate is a sample snapshot and that there is uncertainty around it that depends on sample size and variability. When sample sizes are large, the rate estimate becomes more stable and your confidence interval narrows, making decisions easier. DataX rewards learners who can connect the theorem to rate-based decisions because it shows you can apply statistical foundations to real metrics. A frequent confusion is mixing the central limit theorem with the law of large numbers, and the exam may test whether you can keep them conceptually separate. The law of large numbers says that as sample size grows, the sample mean tends to converge to the population mean, which is a statement about where the average goes. The central limit theorem says that the distribution of the sample mean, properly scaled, tends to become normal, which is a statement about how the average varies across samples. One is about convergence to truth, and the other is about the shape of uncertainty around the estimate. You can have convergence without having a normal approximation be useful at small sample sizes, and you can have a normal-shaped sampling distribution while still having uncertainty about the true mean in any particular sample. The exam rewards this distinction because it prevents sloppy reasoning about big samples solve everything. When you can state that one theorem is about accuracy in the limit and the other is about the distribution of averages, you are demonstrating correct foundational understanding.
When assumptions feel uncertain, bootstrapping becomes a practical companion to central limit theorem thinking, and the exam may reward recognizing that connection.
Bootstrapping uses resampling from the observed data to approximate the sampling distribution of an estimator, providing an empirical way to construct confidence intervals without relying as heavily on parametric assumptions.
In situations with skewed distributions, unknown shapes, or unclear conditions, bootstrapping can offer a more robust view of uncertainty, especially when sample sizes are moderate and the central limit theorem approximation might be questionable.
The exam typically does not ask you to implement a bootstrap, but it may ask what approach is appropriate when normal assumptions are shaky. Recognizing that bootstrapping is a way to estimate uncertainty directly from the data reflects mature reasoning about inference. It also aligns with the broader DataX theme that methods should fit data conditions rather than forcing assumptions that do not hold. When you connect bootstrapping to central limit theorem boundaries, you can choose answers that reflect responsible uncertainty handling.
Ultimately, the central limit theorem is valuable because it helps you translate sampling behavior into decision confidence for stakeholders. Stakeholders rarely want a theorem. They want to know how certain you are and how much risk is attached to acting on a result. Central limit theorem intuition supports explaining why larger samples produce more stable averages, why uncertainty shrinks with more independent data, and why confidence intervals provide a sensible way to communicate that uncertainty. It also supports explaining why some conclusions should be cautious, such as when data is highly variable, heavy-tailed, or dependent, because those conditions reduce stability. On the exam, this often shows up as questions about whether evidence is strong enough to act, whether more data is needed, or what caveats should be communicated. DataX rewards answers that show you can communicate uncertainty clearly without freezing, meaning you can recommend action with appropriate caution or recommend additional data when the current uncertainty is too large. When you can tie the theorem to communication and decision-making, you are using it the way a seasoned practitioner does. A useful memory anchor is that averages smooth noise, but assumptions still matter, because it keeps you from treating the central limit theorem as a universal permission slip. Averages do smooth random variation, which is why aggregation is so powerful and why many inference tools work. However, the smoothing depends on independence, on having enough samples relative to the variability and tail behavior, and on not being dominated by systematic bias. This anchor helps you remember that sample size is not the only factor, because dependence and heavy tails can slow stabilization, and bias can make you confidently wrong no matter how large the sample is. Under exam pressure, this anchor guides you to check the key conditions quickly and to choose answers that respect uncertainty rather than overselling certainty. It also keeps you aligned with the DataX preference for disciplined reasoning over slogans. When you can say that the theorem supports normal approximations for means under the right conditions, but that those conditions must be verified, you are answering at the level the exam expects. To conclude Episode 17, explain the central limit theorem once in simple terms, and then apply it to one case, because that is the fastest way to prove you can use it rather than recite it. State that averages of independent observations tend to have an approximately normal sampling distribution as sample size grows, even if the underlying data is not normal. And emphasize that this is about the mean, not about the raw distribution becoming bell-shaped. Then apply it by identifying whether the scenario has enough independent observations and whether variability and tails suggest you need more data for stability. Connect that judgment to whether normal-based confidence intervals or hypothesis tests are reasonable, or whether you should consider robust or resampling approaches when assumptions are uncertain. Finally, translate the result into a decision stance, such as being more confident with a large stable sample or being cautious when dependence or heavy tails are present. If you can do that smoothly, you will handle DataX questions that rely on central limit theorem intuition with calm, correct reasoning. Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.